Right, so we gave in the last lecture a very informal introduction to the ideas of what calculus is concerned with. Right at the end of that lecture, I introduced this notion which I referred to as the first derivative of a function. So what we're going to do in this lecture is look at a little more detail about what the first derivative of a function is and how we can go about computing that. So I'm going to start off with perhaps a rather artificial example problem. So in this case here, we have an object, let's say it's an arrow. It's launched at the starting position and travels in a path that reaches a maximum height at some point here, and then it returns and lands. So what's the problem that we're dealing with here? Well, to recap the setting, we have an object, an arrow say, it's launched at some angle, 60 degrees in this particular case, and it lands some distance, 400 meters, measured horizontally, away from its starting position. Now, suppose we have a function that describes the height this arrow has reached after it has traveled some distance, after it's traveled, say, X meters. What we want to know is what's the highest, the maximum height that that object achieves. And we'd also like to know what the horizontal distance it travels is when it reaches that height. Now we know already that for the starting point and the ending point, that height is equal to 0. So here's a rather crude analysis of how we might tackle that problem. Let's think of the path that our object follows as consisting of two lines. One from the starting point to the point where it reaches its maximum height, and one from the point where it reaches its maximum height and then lands again. We don't have to stop at two lines. Suppose we expand that approach and look at 4 lines. So from the starting point to some midway point before it reaches the maximum height, from that point to the point where it reaches its highest height, from the point with the highest height to some midway point on its descent, and then from that midway point on the descent to its landing position. And we don't have to stop at 4, we could go on to 8, 16, 32 lines in exactly the same sort of breakdown. Then one thing we see is if we look at the gradient of those lines, this in fact is mimicking, it's following the path that is followed by our object as it moves along the line. And another very important point, which is the one we're going to be looking at detail, is when that gradient is 0, then what we have is a line which is horizontal, which is parallel to the horizontal axis. And at that point, the height is maximal. So I'll let you think about why that's actually the case. And to summarize what we have, we are looking for a value moving along the horizontal axis when the function describing the path reaches a maximum height, when it reaches this height h. And this will be when the gradient of the line touching this point on the path, when that gradient is 0. So the question we now have is, how do we construct the function that defines gradients of lines touching a point on a curve? Touching, in this case, this point here. Well, we know how to find gradients. We saw that in the last lecture. We know one point on the line that we are interested in, namely this point here, for the maximizing value. Suppose we choose some point which is very close to our point of interest. Let's say in general, some point t plus some small distance h and the value of the function at that point. Then what we might think is that the gradient of the line between this point and the point we're interested in, that's got to be very close to the gradient of the line touching the point we are interested in. So, a few statements of the obvious. What is the closest point to the point of interest, to this one here? Oh, fairly obviously, it's the point itself. What value in terms of this abstraction we had on the previous slide does this correspond to? Again, fairly obviously, it's the value 0. So let's look at the gradient analysis we get from those two pieces of information. We are looking for the gradient of the line touching the point of interest, and that gradient is the gradient of the line connecting the point of interest to the point of interest. We know how to find that. It's just this. Take the value of the function at the horizontal distance, we subtract the value of the function at the horizontal distance, and we subtract the difference in the horizontal measure that we've travelled. And that we get 0 divided by 0. And mathematicians, formalists, don't like division by 0. It's rather suspect as a process. Well, more frankly, it's just wrong. Okay, so how do we get around this? What's the alternative to the obvious approach? Well, instead of looking at a treatment that gives us a division by 0, let's look instead at how this gradient function behaves as we use smaller and smaller values of h, the place close to our point of interest. In other words, that gradient function, well, we take the value of our function at the point close to the point of interest, and that gradient is given by this expression here. And in order to capture the notion of getting closer and closer to the point of interest, we use this notation here. We write the limit as h approaches 0, the value of the function at t plus h minus the value of the function at t divided by the length separating those two places. So what does that give us? That may not seem to help us with our problem very much. Let's look at a worked example. The specific function, the function corresponding to raising the input value to the power 2, squaring the input value. So, what we had, going back to the expression we had on the previous slide, this reduces to this expression on the left hand side, and if we expand that, we expand this term, then we get that. Here's our function value at the point we're starting with, and we're dividing that by this term here, so we get this expression, the term that we start analyzing, this produces this on the right hand side. And if we go a little bit further, well, this term cancels with this term, so we are left with this expression here. And we go further still. In this expression, we have a term h on the denominator, and we have terms involving multiplying by h on the numerator. We don't need this. We can cancel this term with that. We can cancel this term with that. And so when we do that, what we get as a result is this expression here. And this term here doesn't involve any division by 0. In fact, it doesn't involve any division whatsoever. So as we let this value become arbitrarily small, the outcome of this term here is just a function 2 multiplied by x. So what have we done here? What we've done is determine that the function that describes the gradient of lines which touch the point x squared, when we're looking at the function x squared, that function describing the gradient is 2 times x. And the way we refer to that is as the first derivative of our function. So we write this by saying that when the function we are dealing with is x squared, its first derivative, which we write as f dash of x, that is a function 2 times x. So I'm going to introduce a little bit of notation. This phrase, the function describing the gradient of lines touching the point x, f of x, that's a bit verbose. We'd like to have something a little bit terser. And the way we refer to that function is, as I said, we call that, the function describing this behavior, we call that function the first derivative. And there are two quite common notations that are used. The one that I've been using on the previous slide, this f dash of x notation. The other one, which is quite common, which uses the convention of writing a function in this form, that's this dy by dx notation. Some of you who may have studied mechanics at school or physics may have seen this x with a dot over it notation. It's still used mainly in mechanics and some older physics textbooks. This is a notation that Newton, one of the co-discoverers of calculus with Leibniz, used in his presentation. So what I've just presented, just to summarize, raises a couple of questions. In general, if we want to look at how a function behaves, we study its first derivative. And the first derivative, as I've just described, this is a function. The first derivative of x squared is 2 times x. 2 times x is a function of x. It's a function, and from what I'll call first principles analysis, it's a function that is discovered by analyzing this expression here, by analyzing this. So you might think, well, do I always have to go through what can be quite a complicated process to discover the function corresponding to the first derivative? Do I have to work through the sort of analysis that I did on the previous slide with respect to a quadratic function? Well, the second question, of course, is not only do we always need to go through that analysis, can we in fact always analyze the derivative of a function by working through things in this kind of manner? Well, as answer to the first question, do we always need to go through this process? Well, the answer to that is we don't. There are standard rules we can use as shortcuts to discovering what the first derivative is. I'm going to give some on the next slide. They are also given on this stage of the textbook. As regards to the second question, can we always analyze the behavior of a function? The answer to that is, well, we can't always. There are some functions which are ill-behaved at a particular point that we're analyzing. So two simple examples of that: the function corresponding to 1 divided by its input value. When that input value is 0, that function is not well behaved. For the more involved example, when we're looking at the logarithmic function, when we are looking at the logarithm of something whose value is less than or equal to 0, once again, that function is not well behaved. Some basic rules for finding a first derivative. I'm not going to go through these in detail. As I said, they're in the textbook, and obviously they're on this particular slide. So we have things such as the constant rule, rule for adding functions, rule for multiplying two functions, a very important rule which is called the composition rule, and this is for finding the first derivative of a function of a function. We have rules for dealing with arbitrary powers of the input value, rules for logarithm and for the exponential function, rules for trigonometric functions, and quite a complicated rules for dealing with what I refer to as rational functions, finding the derivative of one function divided by another function. As I said, I'm not going to go through those in detail. You should look at those in the textbook or on the slide. So here are some examples. Suppose our function is x squared plus 2 multiplied by x plus 5. We want to find the first derivative of that function. Well, we use the power rule. X squared, the derivative of that function, is 2 times x. The derivative of the function 2 times x, this term here, that is 2. The derivative of 5, that's a constant, so it disappears. So the first derivative of this function is the function 2 times x plus 2. Well, the more complicated example, if we look at the trigonometric function tangent of x, well, we know from normal trigonometry that the tangent of x is the sine of x divided by the cosine of x. We have rules for differentiating these two trigonometric functions, and we have rules for computing the derivative of one function divided by another function. And so what we discover from that is the derivative of the tangent of x that corresponds to 1 divided by the cosine of x squared. So this is using the quotient and trigonometric rules. Well, the more complicated yet example, suppose we have this function, 1 plus 5x squared, the whole object cubed. Well, here we apply the chain rule, so we multiply the term in brackets by 3. We get this structure here. Because we're applying the chain rule, we have to subtract 1 from the power we're using, and then we multiply this whole object by the result of differentiating the term inside the brackets, and that gives us this term disappears, and we have 2 times 5x, 10x, and if we simplify this, then we get this as the outcome of applying the chain rule to discover the first derivative of that particular function. So where are we going to use this? How are we going to combine all of this? The starting motivation, we phrase that in terms of solving an optimization problem, finding the maximum or indeed the minimum value of a particular function. And in order to do that in depth, we need to look at this notion of first derivative in a little more detail. In particular, we have to look at how we classify what are called critical points of the function, and indeed what critical points of the function are. The tests that these offer us, these provide some very basic but quite powerful techniques for solving optimization problems. And that's a topic that I'm going to move on to in the next lecture.